The subject of this video is to give some details about the poster which will be present at the Mixing Conference in Toulouse in September 2018. So I'm doing a PhD thesis at the University of Liège and I'm supervised by the professor Andreas Fennick. And this poster talks about the influence of ions on the coalescence behavior. The poster is divided in 4 different parts. You have the introduction, the simulation aspect with the modeling, you have the experimental part and the first results. So for the motivation of this study, actually continuous settler is an equipment which is present in many kinds of industries. And this equipment is well designed when at the end of your equipment you have 2 fully separated phases. However, coalescence is really influenced by trace components and impurities like salt. So if you add a small amount of salt in your system, the coalescence behavior will change, so the design of your equipment will change. And as it's difficult to quantify the influence of these impurities, an experiment has to be done in order to characterize the system. And this experiment can be done in a settling cell. Then, from this characterization, you can use a simulation tool in order to optimize the design of your equipment. And in this simulation, the challenge is focused on the coalescence model. So in my case, the simulation tool that I developed is based on redrop. So the simulation evaluates the settling of my dispersion and it evaluated by considering each individual drop. So he creates the system and he evaluates for each drop the velocity to evaluate the new vertical position and then evaluate if coalescence occurs between the drops. And this step is done at each time step. So you have a time loop. At the end, this is the kind of result that you see. So you have the height of the settling cell, you have the time, and the cause scale represents the local holdup. One particularity of this simulation is that the horizontal position of the drop is random. So we don't know exactly the horizontal position of the drop. So we apply a Monte Carlo approach to deal with the statistics in this simulation. Another point that I wanted to talk about is the initial drop size distribution for the simulation. I can use the one that I measure experimentally with the SOPAT probe, or I can use a theoretical one like the normal distribution or the log normal distribution. And another aspect is that I can consider an additional dispersed phase as gas bubbles or solid particles. So inside my simulation, I have my coalescence model. So this coalescence model is based on the observation made by Camp and Kopriva. So when the drop settle, they have a certain chance to enter in collision. This is characterized by the collision rate. Then, when they enter in collision, they can bounce if the relative velocity is too high. In this case, I assume that the coalescence cannot take place. So you have the second parameter, which is the bouncing probability. So if the drop enter in collision and if they don't bounce, they have a chance to coalesce. So this is characterized by the coalescence probability. These variables depend on the contact time and the coalescence time. So the contact time is the time that the drop stays in contact, and the coalescence time is the time that the drop needs to coalesce. The 3 variables here depends on the fluid dynamics, and the coalescence time depends on the material system. So, in parallel, Schoring and Fennick show that a link exists between the salt concentration and type and the settling time. So, the presence of salt influences the DLVO force. So, the DLVO force is the addition between the van der Waals force and the electrostatic force. And one big point of this model is to implement the DLVO theory in the coalescence model. So once I do a simulation, I will compare the simulation with experiment. So the experiment are conducted in a settling cell. So it's a double-wall glass vessel. Inside you place your solvent. In my case, it's paraffin oil and salt water. And inside I have two counter-rotating shafts. They rotate during 30 seconds at 800 rotations per minute to create the dispersion. Then, when the dispersion is created, I stop the engine and I record the settling with a movie camera in order to localize the sedimentation curve and the coalescence curve. I will show you the result after. And also I use the SOPAT probe in order to measure the initial topside distribution, which is an important parameter for my simulation. So in the first result, I wanted to show the different phenomena that are taken into account in the simulation. So first, I take into account the drop velocity. Of course, I evaluate also the coalescence probability in the closed pack zone and in the sedimentation zone. This evaluation is different because in the sedimentation zone you regard only two drops. In the closed pack zone you have the influence of all the drops around, which push the drop to enhance the coalescence. And this pushing drop is characterized by the hydrostatic pressure, which is also taken into account in the simulation. This hydrostatic pressure is reduced due to the counterflow of the liquid phase between the drop. So the counterflow is also modeled in the simulation. I studied also the packing of polydispersed system and compare that to the simulation. I use also a model for the collision frequency and for the contact time. And this is one of the results that I have. So I do my settling experiment. So I measure the drop size distribution with the SOPAT probe, and I have this kind of graph. So here I presented the Q0. And from the experiment, I also have the sedimentation and the coalescence curve, which is represented here. So you have the height of the cell, you have the time, and the black dot here represents the sedimentation curve, and the black dot here represents the coalescence curve. And then I implement this drop size distribution in my redrop program, and I play with the parameter of the coalescence to fit the simulation to the experiment. And this is what it looks like. So the color scale represents the local holdup of my simulation. So the next step here is to implement the DLVO theory in the coalescence model and see and look at the simulation and the experiment to validate the model.